So for homework 3, part B, question 2, we're going to take the equations that we found in part 1 and put numbers to the expressions so we can get actual answers. My piece of paper here with the equations on it, so you can see. So that is what I will be using to do this. So I have the question in here again. So there are 3 open air tanks with cross-sectional areas of 1.5, 2, and 2.5 meters squared respectively. The drain from the bottom of each tank has an area of 0.01 meters squared, exits into the atmosphere and gets collected into a subsequent tank or to the atmosphere for the final tank. The inlet to the first tank, Qn naught equals 0.03 meters cubed per second, which has been made for a long time and is suddenly increased by 10%. Excuse me. We're going to solve the set of differential equations using scipy.integrate.solve IVP, and we're going to plot how the height changes. So we're going to start this with import numpy as np. We want scipy dot integrate. There we go. We're going to import solve IVP, and then from plotly dot subplots we are going to import make subplots so we are able to plot this later on. Now to actually delete that one, go here, to plug in our variables. We are going to have g, which is the acceleration due to gravity, which is 9.81. We're going to have a1, which is our cross-sectional area of tank 1, which is 1.5. We'll have a2 for tank 2, which is 2, and then a3 for tank 3, which is 2.5. We're going to have little a for the hole at the bottom of all of the tanks. Those are all going to be equal to each other and equals to 0.03. We are given Qn naught, which is, this is 0.01, this is 0.03. And then those are all the variables we're given. We want to define our initial heights, which we aren't given, but we aren't given a specific height, but we're told it's in steady state, so we can use the expression to find, we can use the expressions found for Q to write initial heat of fluid. That makes sense. So we have H1 naught, which is going to be equivalent to Q in divided by that little a1, and then that value squared divided by 2 times g. And this will be the same for all the other ones, just changing that little a. So equals Qn divided by a2 squared divided by 2 times g. And the same for tank 3. It's going to be this. Qn divided by little a3 squared, then that divided by 2 times g. Okay, so those are going to be initial heights of all of our tanks. And then we want to change the initial flows so we can get new heights. So we need to define the set point and the height, so we need to find the set points for height of tank 3, and then we're going to have our controller gain as well. So we'll have H3 set point, which is going to be equivalent to 1.1 times the initial height of tank 3, and then our controller gain, which is 0.25. So then to start creating a vector of our tanks, we're going to define RHS in terms of TV, and then we'll have H1, H2, H3, which are all going to be equal to V, and then we'll have the error, which is equal to the set point of tank 3 minus H3, and then we're also going to have our initial Qin, our flow rate in, which is Qin naught plus plus controller gain times our error. It's going to be our flow rate in, and then to write all of our equations for flow, we're going to have Q1, which is equal to the square root of 2 times G, square root 2 times, I'm going to relax down, 2 times G times H1, close that out, and then times little a1. And then doing it for the other two, we're going to have Q2 and P dot square root of 2 times G times H2, and then times A2. And for tank 3, NP square root of 2 times G times H3. Don't forget the parentheses, and then times A3. So now that we have those, we'll return an array of okay, so then we will return, we'll have our Qn minus U1, and then send in, put that one in parentheses here, that'll be divided by big A1, and then we'll have Q1 minus Q2, which should be in parentheses, Q1 minus Q2, and that would be divided by big A2, and then we'll have Q2 minus Q3 divided by big A3. That should be the end of that. So then we'll put a resolution, goes solve IVP of RHS. Oh, I forgot something. So we'll also need 10, which is going to be equivalent to 5,000. So then down here, solve IVP that 0, 10, and then the array of H1, no, the initial height, H1 naught, H2 naught, and H3 naught, just like that. And then we will need comma dense output equals true, comma method equals grade you. Yeah, I think that's right. Okay. So then we have that. Now that we have that, we are going to start plotting. So we're going to have t-plot, which will be equivalent to np dot linspace of 0, 10, and say 1,000, and h1, h2, h3 that are going to equal res dot the t-plots, and then we can do our subplots. So that would be, those are with the figures, so figure equals make underscore subplots, and then we're going to do one for each, a scatter for each of the tanks. So our x is going to be our t-plot, our y is going to equal our h's, and then we're just going to name each one based off of what tank it is. Tank 1, oh, I need those. Tank 1, and then do the same for the other two. Scatter x plot, oops, x equals t plot, y equals h2, and then the name is gonna equal tank 2. And then do it again for tank 3. Scatter x equals t plot, y equals h3, and the name will be tank 3. Go. And we want to update the layout. So we'll do update layout. We'll change the width to 800. Change the height to 600. We'll leave it just like that. And then let's run it and see what we get. Oh. Let's see. See what it says. Oh. P dot array. Try that. Look at that. There we go. Okay, so that is how we solve homework 3 part B question 2.